let's talk about partial fractions. This video, because it's a class replacement, is going to be a little longer than our normal problem solving videos, but I'll try to keep it as succinct as possible. All right, so I want to start with this line here that just tells us the method of partial fractions that we'll learn in this section. It's not an integration method. It's not like U substitution or integration by parts. It's really just algebra. So it's an algebraic method that reformats an integrand. Specifically, we're working with integrands that are proper rational functions. So a rational function is always a polynomial divided by another polynomial. And what specifically makes one rational is if the degree of the top polynomial is strictly less than the degree of the bottom. So this is something that in another class I might call a bottom-heavy rational. You don't want their degrees to be the same, and you don't want the degree on top to be bigger. It has to be strictly less. We'll talk later about what to do if your rational function is improper, so they're the same degree or the degree on top is higher. You just bust out polynomial long division and reformat before you do this method, but we'll worry about that later. Okay, so we're assuming we're starting with a proper rational function. We have a quick warning in red before we actually see the method here. There are some proper rationals that we already know how to integrate. So if there's another way, then doing the method of partial fractions is super overkill. So for example, something like this is just arctan. Something like this, a quick U substitution for the denominator, would work out really smoothly. So for these ones, you want to use those methods instead of doing partial fractions. Okay, so here's the general idea. Suppose we want to add two small rational functions together. We don't really know why, but this is kind of our starting point. So here I have 1 over x plus 1 plus 3 over x minus 2. Okay, so if we needed to add these together, we would create a least common denominator, which is just the product of these two denominators. And we want to multiply each of these fractions up so that their bottoms match. So this one needs x minus 2 top and bottom. And then this one would get x plus 1 top and bottom. And now we can add across the top because they have matching denominators. So we would have 1 times x minus 2 plus 3 times x plus 1 over that denominator. And you can write those two factors in either order. If I distribute the 1 and the 3, I'll get x minus 2 plus 3x plus 3. I'm also going to FOIL out the denominator just to kind of make this look as different as possible from where it started. So I would have x squared minus x minus 2 in the bottom. And then if I combine like terms in this numerator, I would get 4x on the top. Negative 2 plus 3 is plus 1. So I have 4x plus 1 over that expanded denominator. Okay, so what's going to happen to us in the method of partial fractions is exactly the opposite of what just happened. So we're imagining that you're being asked to compute the indefinite integral of 4x plus 1 over x squared minus x minus 2. So we look at that and we say, all right, we have no other methods that really work out here. We recognize that it's a proper rational function. So we're going to learn the method of partial fractions, which helps us backtrack this common denominator work and split it back into these two individual fractions. So I'm going to write PF here just to be like, there's a whole bunch of work that gets us here that we're about to learn. So you'd say, okay, I've reformatted this into 1 over x plus 1 plus 3 over x minus 2. And we know that's true, at least for now, because it's where this all started. And then when I go to integrate either of these, they're both really nice short U substitutions. So this one you would sub in for x plus 1. And then this one as like its own integral, you would sub in for x minus 2. And this would come out ln of the absolute value of this denominator. plus 3 times the ln of the absolute value of this denominator plus c. And this is really nice evidence as well of that partial fractions is not actually an integration technique, right? From here to here, we didn't actually do an antiderivative. All we did was reformat the integrand function into something that then we know how to integrate. All right, so I am actually going to use this same example because we know what the answer should be. We're going to use this as our first example to show the process of partial fractions. Okay, so just to be clear, we are starting with the integral of 4x plus 1, x squared minus x minus 2. Okay, so if we're given this integral, our first step will always be to factor the denominator. That's our first step. You don't need to bother factoring the numerator. In this case, the numerator is linear, so there's nothing to do. But if this numerator were more elaborate, there's really no need to factor it ever. We're just going to leave it as is. So this we're going to factor into x plus 1, x minus 2. So I'll take my original integrand and say, okay, this is the same as 4x plus 1 over x plus 1, x minus 2. All right, and then I say, well, I know through some details that we'll flesh out later in this video, that something like this, looking at its denominator, can be written as the sum of two proper rationals, where this is one little denominator and this is the other little denominator. So we can tell by looking at this that it had this structure. We just don't know, actually point to it here, has this structure. We just don't know that the 1 and the 3 are the numerators. These parts are kind of the mystery we need to solve. So I'm going to put capital A and capital B as my mystery numerators and say, okay, this is something over x plus 1 plus something over x minus 2. And now my mission is to solve for what A and B must be to actually make this add to this. Okay, so we'll talk more about how you make this decision after this example. For now, we'll say, okay, I guess that's believable. So from here, we're going to treat this equals this as an equation and kind of ignore this far left piece. To start solving for A and B, we're going to multiply both sides of this equation by this denominator right here. So both sides get times that common denominator. So over here, it just fully cancels itself out because we've multiplied by x plus 1, x minus 2. And here we get x plus 1, x minus 2. And you can imagine it immediately distributing into these two fractions. And there's cancellation. So on the left, I have 4x plus 1. So over here, I would have a times all this over x plus 1, and the x plus 1's top and bottom would cancel. So what's left is the a and the x minus 2. And that's it, right? The top and bottom x plus 1's have canceled. Something very similar happens over here. So we have b times these terms over x minus 2. The pair of x minus 2's will cancel, and all that's left is bx plus 1. All right, so I chose this example to start with because these partial fractions are fairly small and it makes this step pretty smooth. We'll see more complicated examples later where you have more elaborate cancellation and more terms written out here. But for now, that step goes really, really smooth. Okay, so our next step in this algebra is going to be to essentially get rid of all our parentheses. So I want to distribute the a in here, distribute b in here. So I'm going to mark this as distribute. Just a big expansion step. If there are any like terms, I can combine them, but usually we just end up with a big polynomial on the right. And I'm keeping the 4x plus 1 on the left-hand side as I go. Here I have ax minus 2a, and then bx plus b. So a little extra space here. So from here, we want to really stay on mission. We're looking at a lot of letters. So what we want to do is remember that we're solving for A and B. We're never actually going to solve for X. X is kind of like it's the variable here. So it's like polynomial equals polynomial, and we're solving for coefficient. So to solve for A and B, we're going to try to rearrange the right-hand side so that it has the same form as the left, right? Something X plus constant. So we're going to collect these by how many, like what power of X they have. So the AX and BX will combine into A plus BX. These two other terms are the constants. In examples in the future that have a lot more terms going on, there'll be terms with X squared you can put together, terms with maybe X cubed you put together. So in general, we'll say collect by power of X. So for us, that means put these two together. I'm putting the X on the right so that it looks like 4X. So 4X and A plus BX are kind of matched up. But you certainly could put the X on the left-hand side if that's what your brain wants to do. Right? And then negative 2A plus B is the constant term. I'm actually still going to group them together. These parentheses aren't necessary, but I like them. Okay, so we've collected by powers of X so that the right-hand side has the format of a polynomial in X. So now here's the key. This next step is how we get the X out of here, because again, we're not trying to solve for X, we're solving for the A and B. So 4X plus 1 for any X equals this X plus that. This coefficient has to be 4. This coefficient has to be 1, right? If these two polynomials are identical for every value of X you could plug in, then the coefficients must be exactly the same. So this step here, we are matching up coefficients. And this is the moment where X's disappear. So I'll say, okay, the A plus B, because this is what's in front of X, I'll say, okay, well, that must be this 4 right here. And then this constant term, negative 2A plus B, I say constant because there's no X's at all. That must be equal to the constant term over here, which is 1. And now I have two linear equations and two variables, and the X is no longer in the way. So from here, you're going to solve for A and B in whatever way you remember how to solve something like this. So if you've taken a linear algebra course, you might bust out a matrix to solve this. If you remember the elimination method, you could do that, where you like add them together. What I'm going to show you and what I'll always do in class is the substitution method. So the substitution method says, okay, take one of them. In this case, doesn't really matter which one. Usually you just pick the easier one and you solve it for one of the variables, right? So I'll take this first one and solve it for A by subtracting B from both sides. And I get that A equals 4 minus B. Now I'm going to bring it over here and plug this in for A right here. So I have negative 2, and instead of A, I write 4 minus B. The rest of that equation stays the same. And this is something I can actually solve for the value of B now. So I'll distribute the negative 2. Two B plus 1B is 3B. And I'm also going to add this 8 to the right-hand side to get 9, divide both sides by 3, and I get that B is 3. And now I can send this back up here and say, okay, well, if B is 3, then A is 4 minus that 3. So A must be 1. And of course, the more coefficients you have to solve for, the more elaborate this step is. But this is a nice representative example of the process. So we're not done. We're just done with the partial fractions. I should label this last step here. Solve. All right, so once you get your two numerators for the partial fractions, we're going to come back to this original problem and say, oh, I actually know what these tops should be. So we're going to return to the original integrand, 4x plus 1 over x squared minus x minus 2. Oh, it'd be nice if this was on the screen. Okay, so we said a over x plus 1, and we know that a is 1. So a over x plus 1 plus b, which was 3, over x minus 2. Then from there, we've actually already done the rest of this problem. If we scroll all the way up to the top here, this is the one we were saying, oh, once you can actually write it this way, now you have smaller problems, and it's something that you already have the techniques to integrate. They won't always be a U substitution for the natural log, but this does come up a lot in the answers. So from here, just to finish off this problem, I'll write the answer that we talked about before. And I'm skipping the U substitution steps here because they're fairly quick. Yeah, so this that we just saw is generally the steps that we'll take for partial fractions. It's just the same thing, but messier from here. Before we do another example, which we will, I just want to spend some time talking about how to actually create the partial fractions part. So if we scroll up in this example to this second step here, we said, okay, start by factoring the denominator, and then you split it into the sum of these little fractions. These are the partial fractions in the name. In this particular example, it was kind of believable that this would be one denominator and this would be another. But what if that denominator factors differently? What if there's like an x squared in it, or it doesn't fully factor into linear terms? This step gets a little bit more complicated. So let's talk about the rules. Shift up here. All right, so how to make your partial fractions. So one important rule here is to remember that the partial fractions are proper rationals. The partial fractions in that initial kind of breakup step are proper rationals. And we said a proper rational, it has to have a lower degree polynomial in the top. So anytime you have a linear factor, I'm going to make a little chart here. Factor in denominator, and then next to it we'll have partial fraction. So if you have just x minus some number in the factored form of your polynomial, this is what we had in our last example, right? The x plus 1, the x minus 2. Then the only thing that could be its numerator is just a number. So what we did in that first example is what we would do for any non-repeated linear factor. Right? It is possible that you can't fully factor into linear factors. So you might get what's called an irreducible quadratic. Abbreviate that. So it'll look like x squared plus bx plus c. Very, very often, this just looks like x squared plus a number. Anything like that, you can't factor it further without using complex numbers, which we're not going to do. It is possible to have a center term here and have it not be factorable, which we'll run into in some examples and talk about how to recognize it. So if you do have one of these as part of the factored form of your denominator, then that whole thing is going to be one of the denominators of the fractions. And we said the partial fractions have to be proper, but here the degree of the bottom is 2. So on top, we could have degree 0 like this, or we could have degree 1, and it would still be proper. So we want to leave space for potentially a whole linear function up here. So instead of just a number, we'll say ax plus b. And you're going to solve for the A and B in a similar way as before, and then plot those numbers in those spots here to make a linear function. These are the two most common cases. A couple other things that'll happen here and there are particularly a repeated linear factor. So you have x minus a number. If the number is 0, this is just a plain x, by the way, but then it shows up several times. So it's like raised to the n power. So this would be like x minus 3 squared or x to the 10th power or something. So you're going to start with the normal case here. We say, okay, if it was just to the 1 power, I would have a over x minus whatever that number is. But then you could have also had that thing squared. I'm going to say a1, a2, x minus that number squared, a3 with that number cubed, and you're going to count up all the way until you hit whatever this is. Usually it's not higher than 3, but it could be any number. So we'll just kind of put a dot, 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 go all the way up until you hit whatever that n is. You have to allow for the possibility that any of them could have been there for this to show up in that common denominator. Often when this happens, some of these turn out 0 in the end, so you kind of scrap the whole thing, but you have to allow space for them to have potentially existed. When I do the actual problems, I don't subscript the letters like this. I just do A, B, C, D, until I'm done. But here, it's tough to fill in this last mystery letter if you don't know how many there were. All right, so the final and least common case here in terms of factoring your denominator is if you get an irreducible quadratic factor and then it also has an exponent on it, so it shows up there more than once. So you would have that irreducible x squared plus bx plus c, and then it's raised to a number. And this continues the pattern that we're seeing so far. So you would start with what its just plain partial fraction would have been, which is just something x plus something over that first power. And I'm also going to subscript these for the same reason. And then same thing, you just count all the way up to the factor that's there. So, this shouldn't have parentheses on it. It's just regular linear. So every top here is linear. And then on the bottom, you're counting up powers of this until you hit the power that's actually there. These are our 4 cases. Let me show you some examples of just this partial fractions breakup so that you get a sense of what I mean here. So let's say, paper's kind of distracting. I'm using paper. Okay, let's say your integrand factored into 2x minus 7 over x cubed times x plus 5. Right, so we're past the factor the denominator step here, and we just want to break it into the partial fractions. Very frequently in the homework and tests and quizzes and stuff, this stuff just is its own question because it's an important part of partial fractions. Okay, so here we have x plus 5 as a single linear factor. So we're just going to have something over x plus 5 for this guy. X cubed is the same as x minus 0 cubed. So this is a repeated linear factor. So we have to accommodate for x, x squared, and x cubed here, but they're all just going to have a letter on top. So we could have something over x, something over x squared, something over x cubed. So all these are just for the x cubed. And then x plus 5 has its own fraction here. So in this one, we're not going to totally solve it out, but when you do, or if you do, you're solving for A, B, C, and D. Let's try another. I'll write this one down, 18x squared plus pi. And then the factored form, let's say, is x times x plus 1 squared times x squared plus 2. Pause the video and try the partial fractions breakdown of this, and I'll keep talking through the answer. All right, so I'll go left to right here. This x is a single linear factor. It's really x minus 0. So this just gets an a over x. X plus 1 squared is a repeated linear factor. So we'll start with plain x plus 1 and then count up to the second power. So I need one of them, and then the second. And I'll stop here because this power was only 2. And then here we're seeing our first irreducible quadratic, x squared plus 2. So this can't be factored any farther and staying in the real numbers. To double check that, if you're not sure, x squared plus a number is always irreducible for these purposes. But if it's a full quadratic and you want to check, you could throw it into the quadratic formula. And if the quadratic formula doesn't give any real number answers, then it's definitely irreducible. We'll see that next. All right, so we need a fraction that has x squared plus 2 as its denominator. So because this is power of 2, we could have a whole linear function up here and still be proper. So I will say dx plus e up there to leave space for that. Okay, let's see one more with an irreducible quadratic. I also want to point out these numerators here, especially the one with the pi, they have nothing to do with this step at all. So this 18x squared plus pi had no bearing on our decisions here. It would just be part of the solving later on. It's all about the denominator for this step. All right, the last one, I'll just put a 1 on top since it doesn't matter. And let's say we have x squared plus x plus 1 squared times x to the 4th power. We'll make this one really annoying. All right, so I might double check first that this quadratic has been left in this form because it is irreducible. So let's check. I'm not just going to brainstorm, 2 numbers that add to 1 and multiply to 1. I'm actually going to put this in the quadratic formula. Because if the numbers were just going to be kind of gross numbers, you may not come up with them in normal factoring, but they would come out here. So the quadratic formula says x equals the opposite of b plus or minus the square root of b squared minus 4ac over 2a. So specifically, we're looking under this radical here. 1 minus 4 is -3. Because there's going to be a negative number under this radical, no real number solutions come out of this. That's how you can double check that it really is irreducible. Okay, so we need 2 factors for this guy, one with just the plain quadratic and then one with the square. And each of them can have a linear numerator. So we'll have ax plus b over the regular. And then we'll say cx plus d. I'm just going through the alphabet. X squared plus x plus 1 squared. And I'll stop there because it's squared in my factored form. And then finally, I need 4 partial fractions for the x to the 4th, from x all the way up to x to the 4th. And they'll all have the same numerator as the very first one that starts. So just plain letters on top. E. G, and H. We won't see any that we need to solve by hand that actually have this many mystery letters in it, but this is how that partial fractions breakdown would go. Okay, so I'm going to end this video because it's getting really long with an example. So what I would like for you to do is try this partial fractions problem. So entirely top to bottom, do partial fractions and actually compute this integral. So our example is going to be the integral of 2x cubed plus 4x squared minus 1 divided by x to the 4th plus x squared dx. So you want to start by double checking it's a proper rational, factor the denominator, use the rules we just learned to split this into partial fraction pieces. And then all those numbered steps in red from the beginning of the video, use those to solve and then rearrange. I'm going to end this video here and make a second video that is just me solving this example, and that'll be the second partial fractions video for today.